Good day, everyone. My name is Stephen Carr from the Autonomous Systems Group at UT Austin, and today I'll be describing our work on safe policies for factored, partially observable stochastic games. I'll first begin by describing two motivating scenarios: a paired helicopter for a Mars rover and a drone delivery task with a balloon-based dispatcher. In each case, we are focusing on controlling the behavior of the small UAVs that have to maintain a safety constraint with respect to a larger agent outside of their control, in this case, the balloon and the Mars rover. In this work, the goal is for the controlled agent to achieve the task whilst being safe with respect to this other agent. Let us consider this working example for drone delivery. In this case, Agent 1 wants to deliver an item from one side of the grid to the other, whilst also remaining within the observable window of Agent 2. This environment naturally splits into separable features, where, in one case, only the physical location of Agent 1 impacts the reward, and, in the other, only the relative position dictates the safety constraint. This class of problem is modeled as a partially observable stochastic game, or a POSG. Computing safe policies for POSGs is very difficult, and finding the optimal policy is undecidable. However, if we have a formal separability assumption for the POSG model, i.e., we can separate the state and action spaces based on reward, safety, and partial observability, then we can split this difficult problem into some more tractable subproblems. We call this splitting the separation of concerns. In the case of the presented problems, this involves separating the reward task with the partial observability from the safety task and the adversarial agent. In doing so, we create a partially observable Markov decision process and a fully observable stochastic game. Finding the optimal policy for a POMDP is still undecidable, but the state-of-the-art solvers have made the policy computation more tractable. Meanwhile, finding the maximally permissive policy for a stochastic game can be written as a mixed integer linear program, which is NP-hard. Quickly describing the process flow, we start with a factored POSG and a safety specification. We then employ feature splitting to get the stochastic game. Then formulating this stochastic game as an MILP lets us compute the maximally permissive policy, which will restrict unsafe action choices. Projecting these onto the reward features gives us the POMDP, which we then plug into our solvers to obtain a safe policy. For the Mars rover example, we performed a physical experiment, which, in lieu of a helicopter, we used a wafflebot. And this wafflebot is tasked with sampling 3 locations. In this case, Agent 1 is the robot, and the 3 locations are T1, T2, and T3. The robot can take observations of the rocks at these locations. The green squares represent the potential recharging locations and will change based on Agent 2's goals. The lightning bolt indicates the active charging point at any one time. At each point, the permissive policy rules out actions that would lead to violations. At this point here, the permissive policy removes 2 action choices that would lead to the agent running out of charge. Showing an additional run, here Agent 1 goes to T2 and finds that that rock is not worthy of doing a full sample, and then eventually recharges. Here the completion of the full run results in a accumulated reward of +19. Here we describe how this separable method scales. In the UAV delivery case, we show that for a grid size of 40 by 40 and a window size of 7 by 7, which is a model of 600,000 states, that we can compute a tractable policy. And this is orders of magnitude larger than any existing partially observable stochastic game method. We want to thank you for your time. If you have any questions or if you would like to see the full videos, please view our paper. Thank you again.